You've probably heard of the Doppler effect. It's the effect that we think of whenever we hear a car passing us by or a train passing us by, or anything that causes the sounds to change their pitch as the object passes us by. So let's talk briefly about what that means for sound, and then we'll see how this applies to light. When you are standing by the railroad tracks, a train might blow its horn, and if it does, it's going to send out waves in all directions. And that means that the waves are going to have a characteristic rest wavelength. The wavelengths are going to be the same everywhere. But if the train gets moving down the track, now the waves in front of the train are compressed into shorter wavelengths. Or, since wavelengths are inversely proportional to frequency, the pitch or the frequency of the train's horn increases. But as the train passes you by, you are now listening to the waves that are being stretched behind the train, and so the frequency of the sound drops precipitously. So this is the Doppler shift in a nutshell, and we express the Doppler shift by the Greek letter delta lambda. So it's delta lambda, change in wavelength. But this change in wavelength also applies to light from moving objects. So imagine a star, let's say it's moving in one direction across the screen, and you notice that the light waves in front of the star are compressed to shorter or bluer wavelengths, while the light waves behind the star are stretched out to longer and therefore redder wavelengths. So we call these shifts in wavelength blue shift and red shift respectively to indicate whether or not the light waves are coming toward or away from us. But just because a star might have a blue appearance or a red appearance does not mean that the star is blue shifted or red shifted. It's simply because of the temperature. So how do we tell whether or not a star is in fact coming toward or away from us? What we do is we pass its light through a prism and we generate a spectra. So in this case, we have the absorption lines of hydrogen in the star's atmosphere. So if we compare the star's observed wavelengths to the known rest wavelengths, we can now see what would happen if the star is approaching us. So the change in wavelength is simply the observed wavelength minus the known rest wavelength. In this case, we are subtracting a larger value from a smaller value, so we're going to end up with a negative value of the Doppler shift. Therefore, a Doppler shift is blue shifted to shorter wavelengths when the object is approaching Earth, and therefore its Doppler shift itself is always going to be negative. It's going to be less than zero. On the other hand, if the star is moving away from us, now the spectral lines of the star are going to be red shifted. If we subtract the rest wavelength from the observed wavelength, we now get some positive number. So spectral lines will always red shift to longer wavelengths when an object is moving away from Earth, and its Doppler shift is going to be positive in value. So the velocity of a star's motion toward or away from us is called radial velocity, and we give that a negative value when it's approaching Earth and a positive value when it's moving away from Earth. This means that the greater the Doppler shift, the greater its radial velocity is going to be. Think about it this way. We have two stars here, A and B. Both stars are blue shifted, so their Doppler shifts are going to be negative. However, star B is coming toward us at twice the velocity of star A. Therefore, its spectral lines are going to be shifted to the blue by twice the amount. And this is also true if the stars are moving away from us, right? Star B is moving away from us at twice the velocity of star A, so its absorption lines are Doppler shifted by twice the amount of star A's Doppler shift. So we can relate the radial velocity to the Doppler shift and to the rest wavelength like this. It's simply the Doppler shift divided by the rest wavelength multiplied by the speed of light. So let's run through a quick example here. We're looking at the spectrum of a star, and its observed wavelength of the hydrogen beta line is at 486.11 nanometers. That's just 1/100th of a nanometer different from its rest wavelength. So what kind of a radial velocity does this tiny change result in? Well, let's calculate it out. So we can cancel out the nanometers, and we find that we have 2.01 times 10 to the minus fifth multiplied by the speed of light. Well, the speed of light is 3 times 10 to the 8th meters per second, so if we multiply that out, we find that this star is moving away from us at a velocity of 6,171 meters per second, or basically 617.2 kilometers per second. That is pretty fast, even though that's just a very tiny change in the Doppler shift of the star. So a tiny blue shift or a red shift can mean an enormous radial velocity.